Next speaker of this morning section is Eduard Ortega from Norway, NTNU University, Trondheim, I don't know the pronunciations, correct? He's going to talk about rigidity of LP operator algebras. Thank you.
Thank you so much. First, thank you to the organizers for allowing me to come here and talk. And actually, it's a fantastic place here. It's one of the nicest auditoriums I ever taught in, so it's really a privilege. Okay, so I'm going to talk about, well, some of my research topics that I thought it would fit better in this conference, that is LP operator algebras, and some results on rigidity. So, well, I'm just going to bit overline of my talk. First, I'm going to talk about a little short introduction what is an LP operator algebras. Actually, the examples that probably are more interesting and have further applications are the ones associated to groups. And then I'm going to give like the main technical tool here, that is why in the LP operator algebras, in particular in the case where P is not equal to, they have these nice rigidity properties. That is due to this a theorem from Lampertis that established like the structure of invertible isometries in LP spaces. And at the end, I'm going to give actually the result about rigidity, and I will try to explain what I mean by rigidity of group algebras. Okay, so let's start. So, what is an LP operator algebra? An LP operator algebra, man can think as a Banach algebra that admits an isometric representation in some bounded operators on an LP space, where P is from 1 to infinity. So one of the most famous results in operator algebras is the one due to Gelfand, Neymark, and Siegel that somehow internally characterize this L2 operator algebras, saying that whenever we have a Banach star algebra that has this condition on the norm, that's called that when you take any element, you multiply by its involution, and you make the norm must be equal to the norm square of the element. So this equation that looks like very innocent is telling you that this algebra is automatically some bounded operators on some L2 space, so Hilbert space. Okay, so this gives you a nice internal characterization of the L2 operator algebras, but unfortunately this characterization is not valid anymore, or we don't able to find any characterization of LP algebras where P is different than 2. So we don't have any kind of internal characterization. So we have to, it's more a constructive way. So we detect when an LP algebra is such when we actually can write down this isometric embedding into bounded operators in LP space. So when P is not equal to, the operator algebras lack of the nice properties of the sister algebras, the L2 algebras. One of the most important things are that they don't have the norms usually are not unique, and the image between algebras, continuous image, the image of continuous morphisms are not contractive, something that is automatically in the case of P equal to. Okay, so the case when P is different than 2 is the one that we actually going to focus, because it lacks a little more theory, and the theory is not like as nice, as rich as the P equal to. No. So, okay, group algebras. So what we're gonna make is a construct LP algebras, operator algebras, and the most standard way to do it is giving an object and having a representation on an LP space, and from there construct the algebra. So in our situation, we're gonna take our favorite locally compact group, and actually we're gonna have as well a continuous cocycle. continuous cycle satisfying the co-cycle conditions. And then we're going to construct a representation of this group together with the co-cycle as a map from the group into the isometries on a certain LP space, satisfying these properties. Observe that the pi is almost a group homomorphism. But the problem is that is this factor here that avoids this to be a group homomorphism. Okay? So yeah, and this thing as the isometries of an LP space that we can define them as the elements such that they are invertible and both the element and its inverse has norm 1. Okay, so I want to give a motivation of, well, where these projective representations shows up, and probably, well, this is the example, and probably they come from, a typical example comes from this, from the well representation, and actually this comes from probably the most famous equation in mathematics, that is the Heisenberg commutation relations. Okay, given two self-adjoint operators in L2, they have to be unbounded, satisfying this commutative relation. Okay, so example of this of operator satisfying this property could be like this this Schrodinger representation of these operators that gives like an operator here. You just make the multiplying by the variable, and the other operator is the derivative operator. Okay, these are not bounded operators, but what we can do is exponentiate these operators, and we get like bounded operators. Okay, so we exponentiate these operators P and Q, and what we get here are unitaries. Okay, that depends on a parameter X and Y. So now these are unitaries, so invertible isometries, you want to think, that satisfies this commutative relation. Okay, this is called the wild commutative relation. So once we have that, what we can do is construct a projective representation of the group R2 in this following way. And actually we see that it's projective because the cocycle that appears before can be described in this way. Okay, so the projective representation somehow appears naturally in mathematics. So what we're going to do, but we're going to, given a group, we would like to construct a canonical representation of the group. Okay, and the way we do it is so defining this what is called the left regular representation. So is a map from G to isometries into LP space of the group G. So the SP integrable functions in G. So what we're doing is essentially what this represented does is when you have an element from the group X. So this defines the isometries that mainly what it's doing is the translation of the function by multiplication of the group on the left side. So what it gives you, this representation integrates to a contractive star algebra representation of the L1 as bounded operators on LP space. And actually what we're doing, well, this is an algebra, the L1 G is an algebra with this somehow twisted convolution product. Okay, so we have this L1 is a structure of Banach algebra. And then what we're going to do is define our algebras that we are interested in. And those are like first the pseudo functions. The pseudo functions are just the completion with respect to the operator norm of the image of this L1 algebra by the regular representation. So this algebra has nice features. One of these is that we say that this algebra is always unital if and only if the group is discrete. Otherwise, this algebra is not going to be unital. We will see that it gets some trouble in our way. So to avoid the lack of unitality, we're going to define what is another interesting algebra, that is the algebra of convolvers. In order to do that, we're going to define we take the image of this L1 algebra we have defined before, and we do the double commutant. Okay? This double commutant is closed in the norm topology. This is a closed Banach algebra, but the nice thing here is that it's always going to be unital, because the identity operator, is always going to be in this algebra. Okay? Perfect. So now the question is how much of the group this algebra remembers. So you have this combinatorial object, if you want to think, and you create an algebra. So it may happen that the algebra forgets completely the group. Okay? So this happens sometimes, but not always. So for example, you have two locally compact groups, and we just say, like in the case the twist is trivial, so we just, for the easiest example, we know that the L1 algebras are isomorphic if and only if the groups are isomorphic. So in essential, this L1 algebras remembers the group. And this is somehow with the exponent being equal to 1. But what happens when the exponent is equal to 2? This is what is called a sister algebra, the group sister algebras, reduced group sister algebras. And in general, the group sister algebras forget the group, in a sense that two different groups can give you isomorphic sister algebras. So example, this kindergarten example is the cyclic group with 4 elements and the group with 4 elements and 2 torsion. So, but there's some class of groups where the sister algebra remembers the structure, the groups that are torsion free and abelian. Then the algebra remembers the group, but in general it's not true. Also, there are some nice examples where we have the free group, where the group sister algebra is the free group, actually separates the free groups. And this is to use some other techniques due to like K-theory. So actually what you can compute is the K-theory of these two algebras, and you say they are different, depends on the M and N. So somehow they distinguish the groups. Other examples come from more von Neumann algebras, but I'm not going to go there, where actually this rigidity is, so this is what we call rigidity, okay, that it's actually very rare. Okay, so how we deal the problem in the case. So actually the idea is we want to give like our algebra some invariant that somehow is going to recall the group, that carries with it the group. And these are going to be the group of invertible isometries, or the unitary group of a Banach algebra. When you have a Banach algebra, you define the groups of the unitary group as the elements that are invertible and the norms of the element and the inverse are 1. Of course, important thing here, we need unital, because otherwise invertibility does not have sense. So, so that's why we need to work with this the algebra of convolvers, because it's always unital. We're going to deal the general case of locally compact groups, because if we could just do the same here with the algebra of pseudo functions, but we have then to restrict to the case of the group being discrete. But we don't want that. So actually what we're going to do is the unitary group of the algebra convolvers is remember that this can be represented as a bounded operators in an LP space. So this is just precisely the intersection between the convolvers and the isometries of LP spaces, invertible isometries. And here is where it comes in play this nice theorem due to Lampertis in the mid-50s that characterize invertible isometries in LP spaces where P is differentiable. And well, I just denote essentially. I'm gonna say what the heart of the theorem says that okay, when P is when P is equal to 2, there are a lot of isometries. And essentially because you can rotate elements of the basis. Okay? And this is due to the geometry of the unit ball. In P equal to 2, the ball of, so this is the element with norm is more than 1, has a nice geometrical shape that is like a circle, but for example, with P equal to 1, the elements, the unit ball has this geometrical figure. This means that, observe that you can translate, you can rotate elements here that they will keep preserving the norm. But here, you cannot rotate. Because if you rotate elements, the norm is not norm preserving, so it's not an isometry. So essentially, Lamperti's theorem is that isometries in LP space with P different than 2, what is 2 essentially is a permutation of the elements of the basis. Okay, and scalar multiplication. You cannot rotate elements. And not only this, what it's telling you is that, okay, when you have two invertible isometries, the distance between the two isometries is gonna be big unless you don't have the same rotation or the scalars you're doing are very close. So this will avoid a lot of homotopic equivalence between isometries. So this is what exactly gives you the rigidity that we want. So then we have our result. The result says that when you have a locally compact group G, you can compute the unitary group of the algebra of convolvers. And this is just what is called the Mackey group. I'm not gonna just comment the definition, but essentially as a set, you can think is a product of the group G and the unit and the elements or complex numbers of norm 1. So what do you think? If you think the representation, what is this? These are gonna be are gonna represent the isometries that moves. So you make a permutation between the elements of the basis. And this element here, the scalar is gonna be like the scalar multiplication. So you just multiply by an element of norm 1, so it's not changing. So this unitary group actually recovers very nicely the group structure. And of course, then you make like the homotopy between all these elements, this result is telling you that the homotopy is going to be only homotopy elements when the scalars are very close. So in a sense, what you make homotopy equivalence between the unitary group, the only thing is that you're doing it, but the groups are gonna stay there. So what this is giving you, is the following. Once you are able to determine the unitary groups, that essentially keeps with them the structure of the group. Well, this isomorphism is not only an algebraic isomorphism, it's also topological. Okay, so you have R isomorphic as a topological group. And you're using here the norm, the topology given by the weak star norm. So what you have here is that the result is that whenever you have an isomorphism with the groups, and actually this cocycle are equivalent in the two cohomology group, then what you have is that the algebras are isomorphic. So this direction is clear, and the other direction is the nice result is that because isometric isomorphism between these two algebras gives isometric isomorphism between the unitary groups. So then you can recover the structure of the group in this way. And this is no problem because this algebra is always unital. In the case of this, remember that these algebras are not generally unital unless the group is discrete, so we don't have this characterization. But we do actually some trick here with the algebra of multipliers, so we can actually extend these results anyway. Okay, but So essentially, the rigidity result is telling you that the algebra of convolvers, when P is different, this important, P must be different than 2, because otherwise we don't have Lamperti's theorem. So we have somehow this kind of nice rigidity. And examples as well related with the initial example that is I just put is this wild commutational relations. When you can have a representation of the Z2, and you can just giving like a number, you can define this cocycle, and then define this algebra. Okay, the twisted algebra Z2. This is a very known object called the non-commutative tori. Okay, the tori is extensively used in non-commutative differential geometry, but also in, for example, time frequency analysis and so on. And this gives like this result is telling you that this isomorphism, these two non-commutative tori are going to be isometric if and only if the cocycles are cohomologous, but this is equivalent to saying that the difference between this scalar here we define must be an integer. This is contrasts very much with the case where the C-star situation with P equal to 2, where you can find isomorphic algebras that the parameters are not cohomologous, and definitely contrast with the case with the convolvers algebra, the von Neumann algebra case in a sense, where all these algebras are always isomorphic to the hyperfinite factor, to one factor. Okay, so yeah, so I think that's all what I wanted to say. Thank you so much.
Okay, thank you very much for your talk. And do you have any questions, remarks, comments, solutions? Okay, if not, I have just a small question because, okay, you talked at the beginning about the Gelfand-Neymark theorem. Any subalgebra, C-star algebra can be seen as a subalgebra of the bundle operator on the Hilbert, no? That means the representation you said before, no?
Yeah.
Yeah, but okay, yeah, it's a new problem about instead to consider just subalgebra, there is an open question about if you can see any Banach algebra as the Calkin algebra of a Banach space, not Hilbert.
Yeah.
You know, this kind of, like, okay, Motakis proved that any abelian C-star algebra is star isomorphic to the Calkin algebra of a Banach space. But do you know any other C-star algebra so that you have a representation as the Calkin algebra?
Yeah. No, I would say some results, but it's on commutative.
Okay,
Banach
but commutative is already solved. Okay.
Yeah, you can use this kind of Gelfand theorem to have like a subalgebras of some on some continuous functions on a topological space.
Yeah, okay.
But
commutative is already solved, but yeah. No commutative. The problem is in non-commutative.
No, non-commutative. I'm not aware, and I don't think there is any nice representation of these algebras.
Okay, thank you. Any other questions? If not, let's thank the speaker again.